Welcome, and this is going to be an experiment that you do not have a copy of. So I have attached a copy of it. I'll also be looking at that same copy here. I apologize for the some of the shadows on the pages, but I don't think it will cause anything to happen. What we're going to be doing is creating a molecule that can luminol, which if you treat it correctly, the luminol will then give off light in a chemiluminescent reaction, meaning we will cause a chemical reaction to happen that will produce light as one of the products. So essentially what's going to happen is we're going to have, if you'll remember back to excited electrons, during the chemical reaction, what's going to happen is some of the chemicals will actually have some electrons that go to an excited state. But rather than dropping back down like they normally do quickly, what we will typically see happen is, in this case, the electrons will get trapped and they'll slowly fall back down, releasing the energy in the form of a visible light. So that's a chemiluminescent reaction. What we're going to do is we will create the product, and it is a two-step process. So in that first step, what we're going to do is we're going to take 3-nitrophthalic acid. You can see that formula there, and we're going to react it with hydrazine. Hydrazine essentially is rocket fuel. So be careful with this stuff around any flame at all, and you will have flame this time. It's going to be an open flame, so be careful with this. You don't want to spill any of this into the flame. This isn't pure hydrazine. It's just a 10% solution, so it's really not that bad. Well, that'll create the molecule called 3-nitrophthalhydrazide. So in essence, what happens here is we're going to form a cyclic diamide. And this is an amide group, which is the N to a carbon chain attached to a C double bond O right next to it. It's an amide group. And that molecule then will be treated again with a chemical called sodium thiocyanate. And if you'll see this structure, this is our 3-nitrophthalhydrazide. That will take and reduce the nitro group here that we put on this to an amine group, making this the chemical luminol. And then what's going to happen is, we've got some modification there of, see if we can rotate that. There we go. So what then will happen will be, we'll take the luminol then to make the light. We will react it with a nice strong base, sodium hydroxide we'll be using. You can see here that the luminol, if we look at the structure, we're going to remove one of those H's off of this compound. And then a reaction that still is not really known on the mechanism of it. There's really not a molecule in here that anyone can isolate. You can read different things about it, but it does not seem like anybody knows what this intermediate step should be. Is we end up removing this group with peroxide. We'll be using hydrogen peroxide again. And that hydrogen peroxide will create this ion. And this ion will be we put this little star out here. It's an electrically excited state, this ion. Then it'll emit a photon. So in other words, you get the exact same molecule. You just have the excited version versus the normal version. And that will give off the light. We'll do that back in one of the closets or something like that. Bring your stuff back and we'll do that. So I've ordered some fresh chemicals on this. We're going to see if they're any better than they were last year. The light was a little dull, so we'll see what happens. Well, now the key here is we're going to use about 1.3 grams of the nitrophthalic acid and 2 milliliters of the hydrazine in a large test tube. I'll have these big test tubes for you. Then you're going to put 20 milliliters of water in a beaker. You're going to clamp that tube to the ring stand. You're going to heat over the micro burner. So we'll get out those little miniature Bunsen burners that you should have in your drawer. If we don't, we'll locate them. We may end up just using a large one. And then what you're going to do is heat that until it dissolves. Then you'll add 4 milliliters of triethylene glycol, basically antifreeze. And you add a boiling stone. And you're going to have to use a 250 degree thermometer. They're special thermometers. I've got them in the back room. And remember for me to get those out, because the reds only go to about 150. So we need a special high temperature thermometer. And then this part's the most important part of the experiment. You're going to put the bulb of the thermometer in the solution, but not touching the glass. So you'll have to kind of suspend it up on, we typically have some wires attached to them. You're just going to suspend that up so you're not taking the temperature of the side of the test tube. The liquid will boil somewhere around 120, but just continue to keep heating it until you get that liquid to get above 200. Your goal then is to back off your heat. And what you want to do, remove that burner, resume gentle heating. You want to keep it between 210 and 220 for about 2 minutes. And be careful, it can boil over here and you can burn it and ruin it, and you'll have to do it again. So allow the test tube to get down to about 100, then add hot water. And you want to wait till it gets down to about 100, because if you don't, that water's going to want to just boil right back out on you. And so put in the hot water that you prepared over on the side. Then cool the whole thing to room temperature, collect your crystals, and get a rough mass of them at that point. You do not need to dry it thoroughly, but just get a mass at that point. That's a key component right there. And then you're going to put it back into that test tube. And going to add some more. Now you're going to add sodium hydroxide solution, and until your material dissolves, and then add the sodium dithionite. It'll be a solid. Then pipette in about 10 milliliters of water to wash down the walls. Heat it up this time until it starts to boil. It doesn't matter what the temperature is. Don't use the thermometer as a stir. You can break it and boil it for about 5 minutes. And then you're going to add that 2.6 milliliters of the acetic acid, glacial. Don't use anything diluted. Then you're going to cool it again. Then you're going to cool it in an ice bath. Don't go directly to the ice bath, because you've been up around 250 Celsius, hotter than that on the tube, and you'll crack it. And then vacuum filter using your Hirsch funnel. That'll be your little one. You're not going to make a ton of this stuff. So that little Hirsch funnel with the little flat piece of filter paper that's in the Petri dish. And then you go on to the actual production. So then what you do is, at that point, you're going to, this is your light producing reactions here. You're going to dissolve your first crop of your luminol, and you just weigh about out 40 to 60 milligrams of what you made. Put that in with 2 milliliters of 3 molar NaOH solution, and then 18 milliliters of water. Call that A. And then B, I'll have the 3% aqueous potassium ferricyanide, and I'll have the 3% hydrogen peroxide. And then you just mix that with water. Now, take 5 milliliters of what you made, mix it with 35 milliliters of water, and then bring me solutions A and B, mix them together, and we'll see if it lights up. And then you're a big winner. I've already talked to you about what to do at the ends. So we will see you on Thursday. Some of you did not turn in lab 22, and you have another one due Thursday.